So the last time we were talking about some of these things. So we finished talking about, for example, we did rectifiers. We also did voltage limiters, and we also finished talking about the light emitting diodes and how the light can be detected using the phototransistor. So the first three topics were discussed in the last two lectures. Um, Today we are going to be focusing on Zener diodes. Um, we'll talk about what the symbol is, what its application is, and we'll look at some example problems, followed by doing a Matlab simulation. Not a simulation, but trying to sketch the IV characteristic of a Zener diode in Matlab, which is going to be very similar to how we did it for the 1N4148 diode. So the part number for the Zener diode is 1N751. That's the one that we have. It could be 750, it could be a different number, but the one that we are using is 1N751. So we are going to try to figure out what is the Zener voltage for this diode through experiments and through simulation as well. So let's take a look at its symbol first. So the symbol for a Zener diode. The symbol, first let's see if I can sketch the symbol of a diode itself. So that's my diode, but for a Zener diode, all I'm going to do is I'm going to make that flat line a little bit of a curve there, just to indicate that there is a early breakdown when you are operating in the reverse biased region. So it's still a positive anode terminal there, a negative cathode terminal there. But in terms of the symbol, all that changes is that addition of those two lines, and that's it. But in terms of operation, a few things change here. So for example, if I take a look at an IV characteristic of this particular diode, suppose we have, let's see, I have V Z indicating voltage across the Zener diode on the x-axis. And actually, let me do VD. I'll use VZ for Zener voltage. VD and say ID. So current through the diode versus voltage across the diode. So this guy is going, you know, plus and minus VD here, and the current is say ID here. So in the forward biased region, which is positive values of VD, if this is 0, the positive values of VD, uh, then the Zener diode behaves exactly the same way as the small signal 1N4148 diode. So I can sketch that by using an exponential line like that. So it's going to exponentially increase, and that typically happens around the 0.7 volts value. So it's very similar to how the previous diode operated in the forward biased region. However, in the reverse biased region, we know that when we apply a negative voltage to the positive terminal of the diode, we are going to have almost no current flowing through the diode. Um, Only a little bit of saturation current flows during that time. So what I can do is I can indicate that by perhaps taking a line going there. So I'm simply trying to trace, maybe I can make it a little bit thicker so that we can see it better. So for some amount of time, it is essentially going to be 0, very, very small, but and in an ideal case, it is going to be 0. Very similar to the previous one in the reverse bias region. But when does the reverse breakdown happen? for the normal diode, the breakdown happens around negative 100 volts, or it might be even lower than that. So you have to go way far into the negative voltages to get it to break down. But for a Zener diode, because it is doped appropriately to break down at a much earlier voltage, the breakdown will happen around a value which is convenient for a particular application. So if I can sketch that, it is going to happen around Vz, negative Vz, because now it's in the negative region. It is going to happen around negative Vz. What does that mean? That means that this Vz is actually the Zener voltage. It could be 5, it could be 10, it could be 3.3, it could be any number of voltages. These are going to be on the negative side, but Vz itself is called the Zener voltage. So we are going to say Zener voltage of 5 volts or 10 volts or 3.3 volts, etc. So the main difference is the early reverse breakdown. That's the only difference between a normal diode and the Zener diode. Um, on the positive side, it works the same way. So we are going to try to explore this. Now, let's talk about the application. How is this useful to me? Now, if you think about any circuit that you might have, so when we were using the digital circuits, what did we have? For digital 7400 series ICs, we were building some JK flip-flops and counters and simple logic gates. All of them required VCC, supply voltage of 5 volts, positive 5 volts. So when you have ICs that are maybe expensive, maybe cheap, however, they are crucial to your design, you do not want to damage those ICs by applying a power supply that is non-regulated, which means that it can change in value. It can quickly change from 4 to 5, 5 to 6, maybe 5.2, goes back down to 4.8. So you do not want that to fluctuate. So what do? You regulate that power supply. So how do you regulate a power supply? For a small voltage like this, for like 5 volts, you can use a Zener diode in the reverse breakdown region to do that voltage regulation. As you can see, even though there is a slight change in current, well, actually there's a drastic change in current. There's a small current there, there's a large current there. But even if there is a change in current, the voltage across that diode around that negative Vz remains more or less the same. So that is essentially our voltage regulator. So the Zener diode is very useful for voltage regulation, so that the voltage doesn't change much even if the current changes. Now, you might say, I have the same thing happening on the positive side with 0.7. Why can't I just use the forward biased region to do the voltage regulation for me? And the answer to that is, I don't think there are many people interested in 0.7 volts to be regulated. And if you were trying to do this with 2 diodes or 3 diodes, you would get a multiple of 0.7 as your regulated voltage, which is limiting to the user. So instead, you use one diode, but in the reverse breakdown region to give you that voltage regulation, which is why Zener diode is useful here. You could also do it with the normal diode in the forward biased region, uh, but you'll have to put a few together depending on what voltage you need to reach, um, and that is essentially the limiting factor here. Okay, so I hope the quick discussion on the symbol, its current voltage characteristic, its application, that is clear to you guys. And now we can move on to the experiment, and mm, followed by Matlab. So if I go on to experiment 8 write up, we have the same things that we discussed just now written up in the experiment background information. Then for the ideal Zener diode, you have the IV characteristic. This the current over here rises at 0 volts. That's for ideal case, but in reality that happens at 0.7, and it does not just go up straight up, it goes up exponentially. So this is just for the ideal Zener. And on the reverse side, around negative VZ, it breaks down, which is typically a much smaller value, like maybe negative 5 volts, for example. So the things that we discussed, you can also read it on page number 16 for some clarification if you need. Let's move on here. On page 17 of experiment 8 write-up, we have a capture PSpice simulation to run. We are essentially taking a DC voltage source, and we are doing a DC sweep. So if you can see here, there's a DC sweep analysis where we change the voltage from negative 10 to plus 10 in increments of 0.1. Yesterday, during office hours, there were some questions about this. It turns out that if you go only from negative 10 to positive 10, you might not be able to explore all the knee current. So you might not be able to go down to say negative 5.1 volts. So what I would recommend is change this. Instead of going from negative 10 to 10, go negative 30 volts to 30 volts. So if you increase the range over which you are running this DC sweep analysis, you might be able to explore a bigger range of the reverse biased voltages. So if you are only able to get the results until negative 5 or negative 5.05, you will be able to go down to negative 5.1 if you increase that parametric sweep range. So that's one quick note that I would like to share. After that, it's pretty straightforward. You simply follow the directions, and you change the axis in such a way that you have current on the y-axis and you have voltage on the x-axis. So the instructions over here will guide you through that process. But eventually, after you do this, all of these steps, you should be able to you should be able to see a graph that looks similar to the one that we have drawn here. Um, let's go back and let's talk about the hardware implementation. So now we are going to put up a circuit. This is going to be very simple. We are going to look at 1N751. That's our Zener diode that we are going to use. And again, we are going to use a current sensing resistor to measure the current through the diode. So we'll do a math channel. So we'll take a voltage across the resistor and we'll divide it by the value of the resistor to get the current through the resistor, which will also be the current through the diode. So the circuit that we are going to build is in figure D-4. So we have a wave gen connected to a resistor of value 1K. So this is going to be our brown, black, red resistor. And we are measuring the voltage across the resistor on channel 2 of the oscilloscope. And then we have a Zener diode D3 with part number 1N751. We are using channel 1 to measure the voltage across the diode D3, and we also have an offset that is provided by the positive power supply here, V plus, the red wire from our analog discovery, so that we can explore a bigger range of voltages. So we are going to set up the circuit, then we will try to do some experiments in order to sketch the current voltage characteristic of this Zener diode in Matlab. So let's first do the experiment. So I'm going to move my things a little bit so that I can set up the circuit. Bear with me for just a bit. All right. I hope you are able to see. Oh no. Okay, so that should be good. And okay. Now on a separate screen, I'm showing the proto board. What I have over here is WaveGen coming in through the yellow wire. Right there, you have the wave. Maybe a different color here. Okay. So I have WaveGen that is going to be supplied through this yellow wire here. From that point, I have a 1 kilo ohm resistor from WaveGen to a different point, and then I'm going to jump that to a place where I connect the blue diode here. So right now I have the Zener diode in the blue color. Not it can be in different colors, but the new equipment that we got for Zener was with a Zener with a color of blue with black markings on it, which is honestly much easier to read. So we have the Zener diode. The positive is pointing up. The cathode with the black ring is pointing down to this connected to this bottom rail where I am going to supply power. Oh, instead of white, maybe red wire is going to be better for this because we are connecting it to the positive supply. Sure. And then what I have is two blue wires here that are measuring the voltage across the resistor R1, and I have two orange wires here that are measuring the voltage across the diode, the Zener diode. So I'm going to hook this up to, so circuit is relatively very simple. You guys have looked at a lot more complex circuitry, so this should be relatively straightforward for you. So I'm going to make the connections here to my analog discovery pinouts and start waveforms. For blue, this guy is supposed to be the negative, that's blue stripe, and I have blue on blue. Okay, so that completes my connections to analog discovery. At this point, I'm going to start waveforms. Okay, so do I need a WaveGen? I think I do need WaveGen. I need scope, yes. So scope I need WaveGen. I also need supplies. So let's work backwards here. For supplies, I'm going to, the write-up says connect the power supply V plus to 3 volts. So I'm going to make that 3 volts, and we'll see the effect of that in just a bit. I'm going to switch off negative power supply. I don't need that here. So power supplies are ready to go. Come to WaveGen. WaveGen is supposed to be set to a triangle wave with 1 kilohertz frequency and 5 volts amplitude. So let's see, 1 kilohertz is fine. Triangle wave and 5 volt amplitude, and then what else? So this is ready to go. Scope. Uh, let's see. For scope, if I wanted 1 kilohertz, that means 1 millisecond. So it should be around 200 microseconds per division. Should be good. And I'm going to set the range of channel 1 and channel 2 to be 2 volts per division because I have uh, a bigger voltage on the WaveGen. So I think this is ready to go. Let's first switch on supplies, then WaveGen, then scope. Okay, so I have let's see, I'm going to increase the plot width here. Then I will I think that's it. Yes. So the blue line is showing us the voltage across the resistor, which you can obtain by simply subtracting the voltage from the source, which is the triangle wave with a 5 volt amplitude. And if you subtract that from subtract the orange line from that triangle wave, then you get the blue line, which is going to be the voltage across the resistor. The orange line, as you can see, is the voltage across the Zener diode. And on the positive side, it is getting limited to 0.7, very similar to the 1N4148 diode. But on the negative side, it goes down to about -5, but around that value, it sort of flattens out. So it's not giving us the good triangle wave as you would expect without diodes present, but it is getting almost like a clipping effect or a limiting effect around -5. So let's actually see what those values are by exploring the IV characteristic. And as we did before, we are going to add a match channel so that we can get current. So I'm going to do add custom math channel, and I'm going to change the equation for my math channel to be channel 2 divided by 1000. Channel 2 because it is measuring the voltage across the resistor, and 1000 because that's the value of the resistor. I'm going to also change the units to amps and say okay. Once I do that, I have a very tiny math channel here, so I'll adjust the range to perhaps 20, maybe even 10 milliamps per division. I can go even further. So 2 milliamps per division, that's going to exactly land on the blue line because 2 volts per division, a factor of 1000 is missing, and since we divided by 1000, they should be the same exact lines. So just to show that they are different, I'm going to make it a little bit zoomed in. So I'm changing the range of the match channel to 1 milliamps per division so you can see it a little bit better. So you're seeing three things here: blue, red, and yellow or orange. The orange corresponds to the voltage across the diode, the blue corresponds to the voltage across the resistor, and the red corresponds to the current through the resistor and the Zener diode. So I guess we are ready to verify the current voltage characteristic in waveforms before we export data to Matlab. So as before, we are going to add this functionality add xy, where you can take one measurement and actually two measurements, and you can plot one versus the other. Let's see here. Going to increase the width so that we can see a little bit better. And the X is channel 1, voltage across the diode, so I'm good with that. Y is channel 2. I need math 1 because that's correct. I will change that to math 1, and that's it. And I hope you are able to see here that it is functioning exactly the same way as the 1N4148 diode. In the forward biased region, it rises exponentially around that 0.7 mark, but on the negative side, around -5 is where it breaks down. So much earlier. In the previous experiment, we were not able to explore this breakdown region, which we are able to do now. So the data looks good, which means that I'm ready to export it to Matlab and sketch it over there. So I'm going to do it like that, and I will say file, export. I'm going to export it as data. I have channel 1, I have match channel. What else do I need? Okay, so this is taking it from source. Okay, I am going to take it from acquisition. So I have time, channel 1, channel 2, math. Okay, that's good. I have all the things that I need. So I'm going to say save. This I can go to my EI directory for experiment 8, and then I can say this is my data for, this is, I believe, figure D4. So figure D4.csv has the data. Okay, my next job is going to be to start Matlab. Matlab is going to take a little bit of time. Okay. So it looks like today we will be done early, because this is essentially the last part of experiment 8. Once we do things in MATLAB, we would have essentially finished the experiment. So look there, that's the checklist. So I feel like we have done reasonably well to stick to our planned schedule. So experiment 8 is due on Monday. So you have a couple of days to put all of these things together. I have already shared the data files, the pictures, all of those things have been uploaded to Piazza. So you can take the data from there. And people have been working already on it already. Many of you have almost finished the experiment write-up, the report. So let's go, MATLAB. I don't know if I should bribe MATLAB to open up faster. All right, so let's see here. I have a blank window in which I can start writing or importing the experiment. Let's see if maybe I can just use the old program, because all that changes now is the experiment. So what I have here is the IV characteristic. Okay. And this is the same program that we looked at in the last class, or the class before that, where we were sketching the IV characteristic for the 1 and 4 on 4A diode. We can actually use the same uh, program, the Matlab script, but we will do some adjustments. So we are not going to be able to do a curve fitting on that. So I don't have this, 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 um, and in fact even this. I don't have a legend. My title will now be for 1N751 Zener diode. Let's see, current through the diode. Maybe I can change this to Zener here as well as over here. Voltage in volts, of course. And let's see, V diode, I diode plotted with the red. Sure. Okay, so it looks good. All I need to do is import it as data. Maybe I'll have to change it, but let's see. So I will go to home. I will say import data. Then okay, what data do you want? I want figure D-4. Figure D-4 is somewhere. Okay. Okay. So when I said import that, it fired up this import wizard, and it is saying that I can import all this data for you as a column matrix. I can actually select numeric matrix because I'm going to separate them out as data for each column. So I can import them individually as time vector, channel 1 vector, channel 2 vector, and math 1 vector, or import it as a matrix. So you will get, I believe, 8,000 something rows and 4 columns. So I'll just do it as a numeric matrix. And then I will say import selection. Once I do that, it is going to start importing the data, and it has finished importing the data. So right now I have figure D4 as 8192 by 4 matrix, and it is in the double format, so I don't need to do the table to array conversion, so I'm good with that. Let's see, time equals data of all rows and first column. No, I need to change that to figure D4. So in order for me to not change anything, I will just say data equals figure D4, and if I do that, then I don't even have to change the remaining statements. Let's see, just to make things a little bit easier to read, and I don't have that right now. Actually, I may need this at some point, so I will just control X this and paste it here. I may need it later. Okay, so that's essentially what my program looks like right now. So I have made the figure equal to data just because I'm using data as an identifier in my code. Then what I said was voltage across the diode is the second column in data, which it is. The third column is the channel voltage across the resistor. I don't need that because I directly find the current through the diode to be the fourth column, which was the math channel. Then I plot voltage on the x-axis, current on the y-axis in a blue dot. Maybe if I can change that to a black dot. Let's see what happens. then I do a hold on, then I do a grid on the plot, then I add those X, Y labels in the title. So I think this is good. I can run it now. Go to editor, run it. Yes, add to path. Okay, so that gives me the IV characteristic of the Zener diode, and from this we can make all the you know we can take a look at where it is going up, where it is doing the reverse breakdown, when is it turning on and when is it doing the reverse breakdown. So by using those data markers, you can do that. So for example, if I do a data cursor here, um, so you can take a look at that. What value is that? So you can read off the X and Y for each of those. Um, so essentially that's about it. So you have seen me write up the Matlab program. So I'm pretty sure that you can uh, do it on your end as well. Can you explain how to find the knee current? So essentially what you do is look at the part number 1N4148, and here let me the details have been written up. Let's see. So I will minimize this. So I hope this was fine. I will share the data with you. Now the question here is, Matthew asked, how do you find the knee current? So if you see this, all you have to do is uh, to determine knee current, you will have to look up the typical Zener voltage for 1N751A diode. So look up the data sheet. The link should be there on the EI webpage. And if it is not, if you have trouble finding it, just Google 1N751A data sheet. And in the data sheet, take a look at the typical Zener voltage. Whatever voltage that you read off of the data sheet, draw a vertical line in the reverse biased region, and at that particular voltage read off the current at that time. The smallest current for which the bias voltage is equal to the Zener voltage is going to be the knee current. I do you see that? So you are essentially saying that if you have, say, a graph like this, you are essentially going to mark a line. I use blue for this. Wherever you have that negative VZ read from the data sheet, and then you are going to find the smallest current uh, that will give you the knee current. So you can do that using Matlab the same way. You can do that using PSpice capture the same way. But earlier I said something about negative 30 to 30 volts. So you may not be able to get to that negative VZ with that negative 10 to 10. And if that happens, then you simply increase that range so that you can explore a bigger uh, x-axis range on this plot, which is why I suggested that you go to negative 30 to 30 instead of negative 10 to 10. Okay. Um, So I shared the data with you regarding the MATLAB plot, and I believe you guys should be able to, add the data cursors here and, for example, even here. So you can take that down and put that over here as well. Um, so uh, I think that's all there is to it. If you want to make it look a little bit nicer, I actually like when I do the export setup. Um, I import a style called presentations. I load it and I apply it. I think I already showed this to you. That appears a much better to me. Uh, So if you guys are interested in using that, please do. So that's your IV characteristic. All right, so I'm going to cross out of this now, and give a quick glance to the experiment tasks. So we did this. We have imported the file. We are plotting Matlab, sure, experimental data. Okay, so that completes experiment 8. Now I will take your questions, and with that we will get ready for a project for demonstration on Monday. Project 4 is really cool, guys. We are going to be optically transmitting and receiving a song. So uh, I encourage you to tune in to look at that demonstration. So um, I'll briefly talk about what the components are for that project. How are we doing the sampling? How are we doing the volume increase and decrease? But we will have the demonstration going on Monday. Okay, let me stop the recording because this is